Okay, so here we are with Unit 12, Lesson number 3, and we're going to be looking at the three main types of natural transmutation: alpha decay, beta decay, and positron decay. Again, what makes something radioactive? It has to do with the ratio of protons to neutrons in the nucleus. And what happens is that the nuclei of unstable nuclei will emit particles in order to become more stable. Those three particles could be alpha particle, beta particle, positron, gamma rays, etc. So let's get into alpha decay. Alpha decay, and before we move on, I just want you to be aware of the fact that, and this does not appear on your reference tables, that an alpha particle consists of two protons and two neutrons. So in essence, it's not really a particle. It's actually four particles stuck together, and that equals an alpha particle. Okay. Now its symbol is, and this is on your reference tables, why do we put the element helium symbol there? Well, it's not the element helium, it's the nucleus of a helium atom, right? Because it doesn't have any electrons. Two protons and two neutrons, that's how many particles are in the nucleus of a helium atom. There are no electrons, but it's just so you're aware. And they don't tell you that the alpha particle is composed of these two, so you should, of course, know that. And you can see here that here's a diagram of an alpha decay. The nucleus, and they only show the nucleus, we don't need to show the electrons because they're not involved in this. This particular isotope of polonium is radioactive. It's unstable. Remember, any element whose atomic number is above 83 is unstable or radioactive. In order to become more stable, it emits two things. Its nucleus will spontaneously give off an alpha particle. When it gives off that alpha particle, it changes into a different element. It's going to change into, this case, a uranium atom. And one of the interesting things about this is that if the new nucleus, and by the way, this is called the parent nuclei, this is what you start with, this would be called the daughter nuclei. If the daughter nuclei is not stable, it will continue to go, it will undergo another decay until it reaches an isotope that is stable. So it could take just one, or it could take several decays or transmutations until it finally gets to a stable nucleus, and that could take anywhere from seconds to billions of years, and we'll talk about that later. Let's take a look at sort of a summary of what happens during an alpha decay. And here's an example of that alpha decay that was above. Here's our parent nuclei, has a mass of 239, atomic number of 94. It decays into two things. It gives off a helium nucleus or an alpha particle, changes into uranium. Excuse me. Notice that it says 24,000 years here. That's something called the half-life, and we'll talk about that later on. So let's take a look. I think it's easier just to do a couple of examples. If you take a look at the first one here, notice that it looks like it's not a complete equation, and it's not. So this is a nuclear, this is an alpha, this is called an alpha decay equation. And you have to be able to complete these equations. Remember, the arrow is an equal sign. If that helps you, then write it, which means that the numbers on this side have to equal the numbers on this side. That's the charge and mass right here being conserved. So if this nucleus gives off an alpha particle, you need to be able to figure out the new element that forms. Remember, this is the parent, that's the daughter. And the way that you do it is you have to remember that this number and this number have to equal the original mass. So 216 must be the mass of the new element, because 216 and 4 gives you 220. The atomic number of the new element has to be 85, because 85 plus 2 will give you 87. So now you go to the periodic table and you look up what element has atomic number 85, and that happens to be AT, astatine. Now look at the second one. They've left everything blank, but that's okay because we know this is an alpha decay. If they didn't tell you it was alpha decay, there is a reference table that you can use to figure out what kind of decay it undergoes, and we'll talk about that in a little bit. And I'm going to write it a little differently because you see how the daughter nuclei is first and then the alpha particle. It doesn't have to be in that order, so I'm going to write the alpha particle first. Again, this is still an equal sign. So I know that this is going to be 218 because 218 plus 4 gives you 222. And I know the atomic number of the new element has to be 84 because 84 plus 2 is 86. And if you look on your periodic table, the element with atomic number 84 is polonium. So that's a couple of examples of alpha decay. Let's do the next one, which is beta decay. So in beta decay, the nucleus gives off a beta particle, and I know that before we said that a beta particle is in essence an electron. It's not exactly an electron, but it's similar to an electron. So when a nucleus of an atom gives off a beta particle, something kind of strange happens. Remember we had said there are no electrons in the nucleus. Well, where does this beta particle come from? Because what actually happens in beta decay is that one of the neutrons actually splits apart. Yes, a neutron is not a single particle. A neutron is actually two particles stuck together. In essence, it is a proton and an electron stuck together. So when you put a positively charged proton and a negatively charged electron together, they form a positively charged neutron. So a neutron is actually these two particles stuck together. So what happens during beta decay is that one of the neutrons in the nucleus splits into a proton and an electron. And this electron that is given off is the beta particle. So it is shot out of the nucleus. But now look at what happens. One of the neutrons has split into the beta, which leaves the atom, but it's also split into a proton, which means now that it had one more proton than it originally had. It got one less neutron, but one more proton. Let's take a look at what we're talking about here. So let's do this. So in this case, that the cesium nucleus has 55 protons. Okay, not sure what's going on here. It's getting huge. There we go. Okay. So again, we said that the nucleus has 55 protons. Oh, God. Try it again. It has 55 protons in the nucleus. And to get the neutrons, you have to subtract these two. So it'd be 70. I believe it's 82. Don't quote me on that. Okay, 82 neutrons. So what happens is that one of these neutrons splits. So now we're going to reduce it to 81 neutrons, right? One of them, and it splits into a proton. So what happens is now the number of neutrons goes to 81, but the number of protons goes to 56. That doesn't change your mass because you're in essence trading a neutron for a proton. So if you look at what happens, this is your parent nuclei, has a mass of 137 and atomic number 55, gives off a beta particle, and it forms a new element. But notice how the mass is the same, 137, but the atomic number went up by 1. Now, if for some reason you can't figure out why that happens, that's okay, because as long as you understand how to do a beta decay, you should be okay. So let's do a couple of examples, and you can look here. Here's one right here. Again, it's the whole rule. The same rule applies before. This is an equal sign. So this is your parent nuclei. It gives off a beta particle. Here's the beta particle. But look at what happens now. You form this new element. But the rule still applies. If you add these two up, right, 56 and a negative 1, so that's like really subtracting 1, comes out to 55, right? If you add these up, it still comes out to 37. So notice the big difference in alpha and beta. In alpha decay, both the atomic number and mass change. In beta decay, the new element has the exact same mass as the original element because all you did was trade a proton for a neutron. Sorry, a proton for a neutron, but the atomic number goes up by 1, and that's what they're talking about here. So let's do a couple of examples, like we had done for the alpha particles. I don't think I'm going to do all 3 of these because we're already up to 9 minutes. So here's the beta particle. I know the mass is going to be 32. Now I know I have to have one higher than my original, so I know this is going to be 16. You go to your periodic table, and the element with atomic number 16 is sulfur. Carbon 14, which is a radioactive isotope of carbon. I'm going to write the beta particle here, 0 minus 1e. I know the mass has to be the same. And I know the new number has to be one more than the original. That's 7. So this is going to be nitrogen. Alright, so that's alpha and beta decay, and I'll do the next ones right now in the next